Работает. Отлично. Okay, so today we begin to study tensor products of C-star algebras. So roughly our goal will be to make the tensor product of two C-star algebras, A and B, into a C-star algebra. And by the way, by the tensor product, I always mean the tensor product over the complex numbers. So our strategy will be as follows. First of all, we start with two C-star algebras A and B, and first of all, we define multiplication on this vector space. And this is very easy. Next, we must define an involution on this algebra. And this is also quite easy, but requires a bit of mathematical culture, mostly because the involution is not a linear map, but is an anti-linear map. The second step is to equip the tensor product with a C-star norm. That is, with a norm which satisfies the C-star axiom. And this is rather non-trivial. In fact, we will see that there are at least two natural ways of doing this. And finally, in general, there is no reason to expect that the resulting normed algebra will be complete. And in general, it is not. So as a final step, we take the completion. And we get a certain C-star algebra, which is called the tensor product of A and B. So this is our plan. Once again, I'd like to stress that the only non-trivial part is here. The non-trivial part is to construct a C-star norm on the tensor product. So let's start with the easy part of this program. So we have the following proposition. If we have two algebras A and B, then their tensor product is also an algebra with respect to the multiplication uniquely determined by the following rule. If we multiply two elementary tensors, A1, B1 and A2, B2, we get an elementary tensor of the following form. The proof is a very simple application of the universal property of the tensor product. So the multiplication on an algebra A is a bilinear map, so it uniquely linearizes through the tensor product of A by itself. So we get a linear map from here to here, which will be denoted by mu A. And now to get the multiplication on the tensor product, we do the following. We take this tensor product, this is a vector space, we tensor it by itself. Then we use the commutativity of the associativity and the commutativity of the tensor product. So we interchange these two factors. So we get the tensor product of A tensor A and B tensor B. And finally, we apply mu A here and mu B here. So we get the tensor product map mu A tensor mu B, which acts to A tensor B. So as a result, we get a linear map of this form. And And this is equivalent to a bilinear operation on A tensor B, satisfying this condition. The associativity of this operation is a simple exercise. This is more or less immediate from the fact that the multiplication is associative on elementary tensors. And finally, the uniqueness of such a multiplication is also immediate from the fact that the tensor product is spanned by elementary tensors. So every element in the tensor product is a finite sum of elements of this form. So this gives us the uniqueness. Okay. Our next step is to define an involution of the tensor product. The delicate point here is that the involution is not a linear map, but is an antilinear map. And to deal with antilinear maps, it's convenient to introduce the following construction, a definition. Suppose we have a vector space E, as usual over the complex numbers. We define the conjugate space. The conjugate space will be denoted by EC of E is defined as follows. As an abelian group, as an additive group, it is identical to E. But the action, the multiplication by scalars is different. If lambda is a complex number and x is an element of EC, then the result of this operation in EC is lambda complex conjugate lambda bar x in E. So in other words, first we apply the complex conjugation and then act by lambda to x. So as a result, we get a new vector space. It's identical to E as an additive group, but as a vector space, it is different. In order to distinguish the elements of E from the elements of the complex conjugate space, let's introduce some more notation. For every element x in E, let xc denote the same element, but considered as an element of the conjugate space. X as an element of EC. So as a result, if we take this standard bijection between E and EC, which takes x to xc, clearly this is a bijection just by construction, and this bijection is antilinear. Antilinear. Just by the definition of, just by this definition. In fact, it can be shown that these spaces are actually isomorphic by using basis, but it's important to understand that there is no canonical isomorphism. If we choose different bases, then the resulting isomorphism will be different. So they are isomorphic, but there is no canonical isomorphism between E and EC. This bijection looks canonical, but it is not linear. It is antilinear. Okay, now we have the following proposition. Here we have two vector spaces, E1 and E2. Then there exists a vector space isomorphism between the complex conjugate of the tensor product and the tensor product of their complex conjugates. And this isomorphism is given by the following formula. If we take an elementary tensor in E1 tensor E2 and consider the respective element in the conjugate space, then this element goes to x1c tensor x2c. So briefly, the complex conjugate of the tensor product is the tensor product of conjugate spaces. The most convenient way of proving this result is to use the universal property of the tensor product. And to recall that, we have to recall that the universal property, the tensor product is uniquely characterized by its universal property. So in fact, it suffices to construct a natural isomorphism, between the space of linear maps from this space to an arbitrary vector space F and the space of linear maps from the second space to F for all vector spaces F. In fact, here I'm using a very special case of the Yoneda lemma, which states that two objects of an arbitrary category are isomorphic if and only if the respective home functors are naturally isomorphic. So in more classical terms, this means that the tensor product is uniquely characterized by its universal property. Okay, so to construct such an isomorphism, we just look, well, let's start with this space, home from this complex conjugate to F. And observe that we can move this letter little c from here to here. Well, this is indeed true because both sets, both spaces, this one and this one, consist of antilinear maps from E1 tensor E2 to F. So they are the same. Now we use the universal property of the tensor product. So this is identical to the space of all bilinear maps from E1 cross E2 to FC. And this is the same as the space of all bilinear maps from E1C cross E2C to F. Well, again, they are both spaces, this one and this one, consist of those maps from E1 cross E2 to F, which are antilinear in each variable, so-called anti-bilinear maps. They are antilinear in each variable. So because of this, these two spaces are identical. And finally, we apply the universal property of the tensor product again, and we see that this is naturally isomorphic to the space of all linear operators from the tensor product of E1C tensor E2C to F. And that's it. So we get this natural isomorphism, and it gives us this isomorphism of vector spaces. So more specifically, if we substitute here for F this concrete space, this one, then the identity map in this space corresponds to this isomorphism, or more exactly to the inverse of this isomorphism. Okay, so now we are ready to define an involution on the tensor product of two star algebras. Our next proposition, suppose that A and B are star algebras Then A tensor B is also a star algebra with respect to an involution uniquely determined by the following formula. Again, we define the involution on elementary tensors, and there is only one obvious way of doing this. To prove that this formula indeed defines, gives us a well-defined involution on the tensor product, we replace antilinear maps by linear maps. So the involution on A is an antilinear map, but it produces a linear map from A to AC, which takes A to A star. And since we replace here A by AC, we see that II is a linear map. This is a linear map. Now we do the same construction for B. And we just take the tensor product of IA and IB. So we get a linear map, IA tensor IB, from A tensor B to AC tensor BC. But now our previous proposition tells us that this is nothing but A tensor B conjugate, A tensor B C. So we get a linear map from here to here. And this is exactly what we are looking for. So this gives us an antilinear map from A tensor B to itself. And now it's a simple exercise that all axioms of an involution are satisfied. This is a simple exercise because basically everything follows from this formula and from the fact that A tensor B is spanned by elementary tensors. Okay, so we see that the tensor product of two star algebras is also a star algebra in a natural way. Okay, so now we are coming to the most interesting part of our program. We want to define a C-star norm on the tensor product. First, let's explain what we mean by a C-star norm. So suppose that A is a star algebra, and suppose that we have a norm on A, and we say that this norm is a C-star norm if it satisfies the following conditions. First of all, it is submultiplicative. Second, the involution is isometric. And finally, the norm satisfies the C-star axiom in the usual sense. And a pair consisting of a star algebra and a C-star norm on A is called a pre-C-star algebra. So the only difference between pre-C-star algebras and C-star algebras is that a pre-C-star algebra is not assumed to be complete. And on the other hand, it's easy to observe that if we take the completion of a pre-C-star algebra, the completion of a pre-C-star algebra is a C-star algebra. Okay, So our goal will be to define a C-star norm on the tensor product of two C-star algebras. To begin with, we consider a very special case of this construction, which corresponds to the situation where one of our algebras, A and B, is the algebra of all square n by n complex matrices. At the first glance, this special case may seem rather artificial. So why do we care about matrices? But we will see shortly that this special case is actually very important. So let's introduce some notation. We denote by Mn of A. So if A is an arbitrary algebra, then we denote by Mn of A the algebra of all n by n square matrices with entries in A. So clearly this is also an algebra under the usual matrix multiplication. If A is the field of complex numbers, then we just write Mn. So Mn is the algebra of all complex n by n matrices. And let's observe that we have an algebra isomorphism between the tensor product of Mn and A and the algebra Mn of A. This is an algebra isomorphism. Given by the following simple formula, you will have a complex n by n matrix alpha ij and an element little a in our algebra. And then this elementary tensor goes to the matrix alpha ija with entries in A. It's easy to see that this is indeed an algebra isomorphism. Clearly, this is a vector space isomorphism. This is quite standard, but a simple calculation shows that this is an algebra isomorphism. So now we have the following proposition. If A is a C-star algebra, then there exists a unique C-star norm on the tensor product Mn tensor A. And this norm makes the tensor product Mn tensor A into a C-star algebra. So there is no reason to take the completion. It is already complete. It is a C-star algebra. And it's also important that this C-star norm is unique. To prove this result, we need the following lemma. This lemma slightly generalizes some of our old results about C-star norms. So suppose that A is a star algebra. And suppose we have two C-star norms. Let's denote them like this. So we have two C-star norms on A. And suppose that A is complete with respect to one of them. Suppose that A is complete with respect to the first norm. I claim that then the norms are actually the same. So let's recall that some time ago, We proved that when we discussed, actually this was at the very beginning of our course, when we discussed spectral properties of C-star algebras, we proved that there is at most one norm on a star algebra which makes it into a C-star algebra. This result is a bit stronger because here we don't assume that A is complete with respect to each of them. We assume the completeness with respect to one of them. And even in this case, the norms are the same. To prove the lemma, let's consider the completion of A with respect to the second norm. Let's denote by A1 the completion of A with respect to the second norm. So it is a C-star algebra. And we have a natural inclusion of A equipped with the first norm into A1. And this is an injective star homomorphism. An injective star homomorphism between C-star algebras. This is a C-star algebra, and this is a C-star algebra. And this is an injective star homomorphism. And let's recall that an injective star homomorphism between C-star algebras is isometric. It is isometric. But this means exactly that the norms are the same. So this completes the proof of our lemma. Okay, now we are ready to prove our proposition. So to construct the C-star norm on the tensor product of A by the matrix algebra Mn, first of all we choose a faithful star representation of A. We already know that such a representation exists. This is not necessarily the universal representation, which appears in the proof of the Gelfand-Naimark theorem. We can take any other faithful star representation of A. So we now take the tensor product by the matrix algebra and consider the tensor product map 1 tensor pi n, which acts from this algebra to Mn tensor B of H. Oh, sorry, this was just pi, yeah. 1 tensor pi acts from A to B of H. This is identified with the algebra of n by n matrices with entries in B of H. And finally, let's observe that this algebra can also be identified with the algebra of bounded linear operators on H to the power n, where H to the power n is just the Hilbert direct sum of n copies of H. Well, indeed, a matrix of operators, a square matrix of operators, is nothing but an operator on the suitable power of H. But this is a C-star algebra. This is a C-star algebra. And this map is injective, because pi is injective. So now we can define a C-star norm on this tensor product simply by applying this map to the C-star algebra. So formally this is 1 tensor pi applied to U. And this is a C-star norm on the tensor product, because it appears from the injective homomorphism to a C-star algebra. Okay, so why is it complete? Let's look at the image of this map, 1 tensor pi. So it follows from the construction that this image consists precisely of those elements in here, U in Mn of B of H, such that each matrix entry of this matrix belongs to the image of pi. Uij belongs to the image of pi for every I and j. And since the image of pi is closed, because pi is faithful, so it is isometric. It is isometric. Its image is closed. This readily implies that this space is also, this subspace is also closed in here. Well, this is a little exercise, but it's quite easy. So everything follows from the fact that the image of pi is closed. And this is a C-star algebra, so we conclude that this is a closed subspace, and so Mn tensor A, which is isometric to this subspace, is complete. So it is a C-star algebra. And now the uniqueness of such a C-star norm follows from the lemma. So we already constructed a C-star norm such that our algebra is complete with respect to this C-star norm. And so the lemma implies that such norm is unique. Now this completes the proof. I'd like to stress that in general we cannot drop the completeness assumption here in lemma. So in other words, if you have an arbitrary star algebra, then there can be many non-equivalent C-star norms on A. And this fact leads to numerous interesting phenomena and complications in the theory of tensor products of C-star algebras. Okay, so as a result, we see that the tensor product of an arbitrary C-star algebra by the algebra of square n by n matrices is a C-star algebra in a natural way. Our next goal will be to extend this construction to arbitrary C-star algebras. Now to define the C-star norm, define a C-star norm, I don't claim it is unique. To define a C-star norm on the tensor product of two C-star algebras, we will need first to discuss tensor products of Hilbert spaces. So we have the following result. Suppose we have two inner product spaces, H1 and H2. So at this point, I don't assume the completeness, just two vector spaces equipped with inner products. I claim that there exists an inner product on their tensor product H1 tensor H2, uniquely determined by the following formula. The inner product of two elementary tensors, Hx1, x2, and y1, y2, is just the product of x1, x2, and y1, x1, y1, and x2, y2. Again, the proof, the most convenient way of proving this is to apply conjugate spaces. Indeed, an inner product is a sesquilinear form. And if we have two vector spaces for each pair of vector spaces E and F, we have a natural bijection between the set space of all sesquilinear forms on E cross F. That is, those maps which are linear in the first variable and anti-linear in the second variable. And the set of all linear functionals on E tensor FC. Simply because the sesquilinear map is a bilinear map from E cross FC. Okay, now to define an inner product on the space, we do the following. We take the tensor product of the space by its conjugate. And we have to define a linear functional on the space. That is a linear map to the complex numbers. Again, we use the fact that the tensor product commutes with the complex conjugation. So this is isomorphic to H1, tensor H2, tensor H1 conjugate, H2 conjugate. Then we interchange these two factors. So we get something isomorphic to H1, tensor H1 conjugate, tensor H2, and H2 conjugate. And now we have, we see that the inner product on H1 is a linear functional on this space. And the inner product on H2 is a linear functional on this space. So we just take the tensor product of the respective functionals. This is the inner product on H1, tensor the inner product of H2. So this map acts to C tensor C, but C tensor C is canonically isomorphic to C. And as a result, we get a linear map, a linear functional on the space, or equivalently a sesquilinear form on H1 tensor H2. So we obtain a sesquilinear form on H1 tensor H2 satisfying this condition. Let it be formula 1. So clearly it is unique, again by the obvious reason that the tensor product is spanned by elementary tensors. So the uniqueness is clear. So to complete the proof, we have to show that this sesquilinear form is actually an inner product, that it is positive definite. Okay, so let's take an arbitrary element U in the tensor product. And let's write it as a finite sum of elementary tensors. yi, zi, say from 1 to m. Now let's write this element in the more convenient form. We look at the linear span of the elements zi. So we have finitely many elements zi, and we choose an orthonormal basis in this linear span. Choose an orthonormal basis that's denoted by, say, E1 to En in the linear span of the vectors Z1 to Zm. If I now decompose each Zi in terms of this basis and rewrite this expression, we get the following formula for U. U can be written as a sum from 1 to n of xi tensor ei, where xi are some elements in H1. And if I now calculate the inner product of U by itself, and use this formula, and use the assumption that EI is an orthonormal system, we see that this is nothing but the sum of the following numbers, the norm of xi squared from y to n. And this is clearly strictly positive if u is non-zero. So as a result, we see that our inner product is positive definite. So this is indeed an inner product. So we get an inner product on H1 tensor H2. And this completes the proof. So now we can take the completion of this space, this inner product space, with respect to this inner product. The resulting Hilbert space is called the Hilbert tensor product of H1 and H2. If we have two Hilbert spaces, H1 and H2, then the Hilbert tensor product of H1 and H2 is the completion. Which is denoted like this. So we put the dot over the tensor product sign in order to distinguish between this object and the algebraic tensor product. So this is the completion of H1 tensor H2 with respect to the inner product given by formula 1. By the way, let's observe that the norm determined by this inner product satisfies the following condition. The norm of every elementary tensor is just the product of the norm of x and the norm of y. So this easily follows from this formula. This means that the norm on the Hilbert tensor product is a cross norm. Is a cross norm. In the general case, by cross norm on the tensor product of two normal spaces, we mean a norm satisfying this condition. Okay, so let's, well, first of all, an initial question is it really necessary to take the completion here? The answer is yes. So in general, this space is not complete, except for the trivial case where one of the spaces is finite dimensional. So more exactly, here's a useful exercise. The tensor product of two Hilbert spaces H1 and H2 equipped with our inner product is complete if and only if either H1 or H2 is finite dimensional. So the tensor product of two infinite dimensional Hilbert spaces, the algebraic tensor product of two infinite dimensional Hilbert spaces is not complete. So the procedure of completion here is necessary. Нет. Here, H1 and H2 are arbitrary inner product spaces. That is, vector spaces, possibly infinite dimensional, equipped with an inner product. No, this is finite, because this is a basis not in H2, but only in this finite dimensional subspace of H2. This is finite dimensional. So this basis is finite. But of course, it's not a basis in the whole space. This is a basis of a proper finite dimensional subspace of H2. By the way, it's rather easy to construct a basis, an orthonormal basis in the tensor product. If we have an orthonormal basis EI in H1, an orthonormal basis in H1, and an orthonormal basis in H2, say Fj, an orthonormal basis in H2, then the collection of all elementary tensors of the form EI tensor Fj over all I and j is an orthonormal basis in the Hilbert tensor product. Well, let's look at some special cases of this construction. Let's look at some concrete examples. Examples and exercises at the same time. First of all, if we take the Hilbert tensor product of H with the finite dimensional Hilbert space Cn, then this is unitarily isomorphic to the Hilbert direct sum of n copies of H. And more generally, if we take the inner product of H by the little L2 space over an arbitrary index set I, then what we get is unitarily isomorphic to the Hilbert direct sum of many copies of H taken over all indices in I. Or this can also be denoted like this. So this is the space of all square summable families in H, indexed by I. Another useful example, if we take two big L2 spaces of square integrable functions on some measure spaces, x mu and y mu, then the resulting space, then the product is unitarily isomorphic to the big L2 space over x cross y. Okay. So now it's natural to ask if this construction, that is the Hilbert tensor product, can be characterized by a suitable universal property, just similarly to the algebraic tensor product. The answer is yes. But at the same time, the class of bilinear maps which can be linearized through the Hilbert tensor product is quite exotic. Such maps are called weak Hilbert-Schmidt bilinear maps. And we'll not discuss this class of maps because it's not very useful for our purposes and because it is rather exotic. Nevertheless, what we are going to show is that the Hilbert tensor product is functorial. That is, it is a functor, it is natural in two variables, x and h1 and h2. To prove this result, let's recall some basic facts from linear algebra. Some linear algebra. So suppose we have vector spaces E1, F1, E2, and F2 vector spaces. And suppose we have two linear maps. S is a linear map from U1 to F1, and T is a linear map from E2 to F2. Then we can form the tensor product map as tensor T, which acts from E1 tensor E2 to F1 to F2. And this linear map is uniquely determined by the following formula. It takes every elementary tensor to the elementary tensor Sx tensor Ty. Well, this is fairly standard. But let's also observe that the meaning of this combination of symbols, S tensor T, the meaning is actually twofold. So this combination of symbols actually denotes elements of two different spaces. Well, indeed, we can look at the space of all linear maps from E1 to F1 and take the tensor product of the space by the space of linear maps from E2 to F2. So S sits in here, T sits in here, so we can consider the respective elementary tensor in this space. But on the other hand, the same symbol denotes this linear operator, which sits in this space. So we have a natural linear map from here to here, which takes every elementary tensor S tensor T to the linear operator S tensor T given by this formula. Let's let it be formula 2. So formally, these are two different objects. One sits in here, and the second one sits in here. But nevertheless, it's a simple exercise in linear algebra to show that this map is actually injective. That's denoted by 3. The map given by 3 is injective. Sometimes this map is called the home tensor interchange. Okay, so these are some basic facts from linear algebra. And now let's show that the Hilbert tensor product is actually functorial, in spite of the fact that we don't want to discuss its universal property because it is rather exotic. Nevertheless, it is functorial. More exactly, we have the following result. Position. Suppose we have Hilbert spaces H1, K1, H2, and K2. Hilbert spaces. I claim, this is part 1 of the proposition, I claim that for every bounded linear operator S from H1 to K1, and for every bounded linear operator T from H2 to K2, the tensor product S tensor T, which acts from H1 tensor H2 to K1 tensor K2. So at this point, I consider the algebraic tensor product, so this is well defined. And what I claim that this map uniquely extends to a bounded linear operator, which will be denoted like this as tensor dot T, between the respective Hilbert tensor products from H1 tensor H2 to K1 tensor K2. And moreover, the norm of this operator as tensor T is the norm of S times the norm of T. And part 2. This construction gives us a natural map from the algebraic tensor product of the spaces of bounded linear operators from H1 to K1 and from H2 to K2 respectively. So this is the algebraic tensor product. This space is mapped to the space of bounded linear operators between the Hilbert tensor products. And this map is given by the following simple formula. And what I claim that this map is injective. Well, to prove this result, let's observe that actually it suffices to show that this map between the uncompleted tensor products is bounded. It suffices to show that S tensor T is bounded and that the norm of this, again, uncompleted tensor product satisfies the following estimate. Well, indeed, if you prove this fact, then clearly this map between, this is a bounded linear map between norm and spaces, so it is uniquely extended to the completions with the same norm. So this estimate holds on the, for the completed Hilbert tensor product as well. And the opposite estimate is a simple exercise. Just apply our map to elementary tensors. If we apply this map to elementary tensors, we can easily get the opposite estimate. So the key point is to prove this. And in proving this, also we may assume, without loss of generality, that T is actually the identity map of an arbitrary Hilbert space H. Well, indeed, in the general case, the tensor product of S and T can be written as the following composition: S tensor 1 and 1 tensor T. So if we prove the result for these two operators separately, then by composing them, we get the same result for S tensor T. So it suffices to consider one of them. For example, this one, S tensor 1. Okay, so why is it bounded? Well, let's take an element U in the algebraic tensor product of H1, and the second space is just H. We write it as a sum of elementary tensors, just like we have already done here. So we write it in this form, where the vectors EI form an orthonormal system, an orthonormal family. A finite sum from 1 to n, xi tensor EI, where EI is an orthonormal family, a finite orthonormal family in H. Okay, then what can we say about this element S tensor 1 applied to U? S tensor 1 applied to U is just the sum of Sxi tensor EI from 1 to n. So the norm of this vector, or better, the square of the norm of this vector, again we look here, is just the sum of the squares of the norms Sxi from 1 to n. This is because EI is an orthonormal family. And this can be estimated as follows. But the sum of the squares is nothing but the norm of u squared. So as a result, we see that S tensor 1 is bounded, and the norm of the separator is less than or equal to the norm of S. And basically, this completes the proof, because we proved this fact in the case where T is the identity operator. Now, the same argument shows that 1 tensor T is also bounded, and its norm is less than or equal to the norm of T. And we multiply these, we compose these two operators, and we get the result. Okay, so we see that the Hilbert tensor product is functorial. Now, let's now discuss Hilbert tensor product of Hilbert tensor products of star representations. So we have the following proposition. Suppose that A and B are star algebras. At this point, we don't assume any norm, so they're just star algebras without any norm. And we have two star representations, pi of A on the Hilbert space H, and tau of B on the Hilbert space K. Star representations. I claim that there exists a star representation, which will be denoted like this. This is a representation of A tensor B on the Hilbert tensor product of H and K. Uniquely determined by the following rule. It takes every elementary tensor, A tensor B, to the operator pi of A tensor tau of B, which was defined in the previous proposition. So it acts from H tensor K to itself. And moreover, if both the representations are faithful, pi and tau are faithful, then so is their tensor product. Well, the proof is very easy. To prove part 1, we just take the algebraic tensor product of pi and tau. This map takes A tensor B to B of H tensor B of K. And now we use this. By the way, I see that I forgot to tell you about the second part of this proposition. But it is immediate from the injectivity of this map is immediate from the injectivity of this map. It's simply the restriction. So this map given here is the restriction of this map to the subspaces of bounded linear operators. So it is injective. This space, by the previous proposition, is embedded into the space of bounded linear operators on the Hilbert tensor product. And we simply look at the composition, and we see that this is exactly what we are looking for. So this is a star homomorphism, clearly. So it is a representation. And also if so this diagram proves both parts 1 and 2, because if pi and 2 are faithful, then this area is injective, because the tensor product, algebraic tensor product of two injective maps is injective. We already know that this one is injective, so the resulting representation is faithful. Okay, now we are ready to define a C-star norm on the tensor product of two C-star algebras. Definition. Suppose that A and B are C-star algebras. And let's consider the universal representations, omega A and omega B. They are universal representations. We define the spatial C-star norm. The Russian for spatial C-star norm is пространственная со звездочкой норма. On the algebraic tensor product is given by the following formula. The norm of an element u in the tensor product is the norm of the operator omega A tensor omega B applied to u. So our previous proposition shows that this is indeed a C-star norm. This is indeed a C-star norm, because we know that omega A and omega B are faithful, so this representation is also faithful, and so as a result our tensor product is faithfully embedded into the suitable space of operators, and we simply take the restriction of the C-star norm here to this subalgebra. And so it becomes a pre-C-star algebra. And the completion of the respective pre-C-star algebra of A tensor B with respect to this norm is called the spatial C-star tensor product. The spatial tensor product of A and B. And it is denoted by the following symbol. So we just put the star as a subscript here. And this is our spatial C-star tensor product. Why is it spatial? Well, because we identify A and B with their operator images, consisting of operators on the respective Hilbert spaces, and we define the norm, which on this algebra, basically this is just the operator norm. This is the norm of the respective Hilbert space operator. By the way, let's also observe that this norm is also a cross norm. It easily follows from the construction. It follows from the construction that the spatial norm of each elementary tensor is just the product of the norm of A times the norm of B. There is an important result about this norm, which is due to Takesaki. So I state this result without proof, because the proof is rather non-trivial, and together with all preliminaries, it will take about a lecture or maybe even more. But nevertheless, let me give you a statement. For every C-star norm, for every abstract C-star norm on A tensor B, we have the following inequality. In other words, the spatial C-star norm is the minimal C-star norm on the tensor product. And because of this theorem, we usually use the following standard notation. Instead of writing the star here, we denote it, this tensor product, like this, and we call it the minimal C-star tensor product. The minimal tensor product of A and B. Совершенно верно. So in the general case, if A and B are arbitrary C-star algebras, I don't claim that these norms are the same. There are some rather natural examples, maybe I'll tell you more about them later, where there are many different C-star norms on the tensor product. In particular, there is another functorial norm, the so-called maximal C-star tensor norm, and in the general case, it is strictly bigger than the minimal C-star tensor norm. But on the other hand, if one of the algebras is good enough, belongs to the class of the so-called nuclear C-star algebras, then the tensor products are the same. But this will be discussed maybe at the next lecture, at the end of the next lecture. Okay, so in conclusion, let's observe that there are two obvious problems, or maybe quasi-problems, with the spatial tensor product. Quasi-problems with the spatial tensor product. The first problem is that it looks uncomputable. In other words, it's impossible to calculate this norm explicitly because it involves universal representations of A and B. And the universal representation is something which is really huge. It is something which involves all states on our algebra. The set of all states is already very big, and the resulting Hilbert space is usually not separable. So the universal, in general, it is impossible to describe the universal representation in reasonable terms. For example, what if we take, say, the algebras of compact operators on two Hilbert spaces? How can we calculate their spatial tensor product explicitly? This is not clear from the definition, at least. And the second problem, the second quasi-problem with the spatial tensor product is that it looks non-functorial. Well, indeed, it would be good to have a functor of two variables, A and B, on the category of C-star algebras. But it's not obvious at all, at least it is not obvious from our definition of this norm, that this is indeed the case. So our first goal for the next lecture will be to show that, in fact, this tensor product is computable and is functorial. But to prove this, we'll need to redefine the tensor product, to define it in slightly different terms. Okay, so that's all for today.